So an important application to integration are distribution functions, okay? And now we're looking at probability, continuous cases of probability. And what do we mean by that? So suppose you throw a point on this line, okay? Where is it going to land? So a point could land here, could land there, could land right in the middle or over here. Well, what's the probability that it lands at any one point? I mean, you might have learned in the past that probability is, say flipping a coin, there's heads or tails. Heads is just one of the two options, so 1 over 2. Well, how many options do you have over here? You have an infinite amount of options. So in a sense, the probability that the point will land at any one point is 0, in a sense, right? How do you remedy that problem when you're talking about a continuous distribution, okay? A continuous number of possibilities, an infinite number of possibilities. Here, rather than talking about the probability of landing at any one point, you talk about it landing on an interval, okay? So in the continuous case, we start talking about intervals. And so we could say that the probability that the point will fall, say, on the interval delta x is approximately equal to, and if delta x is small, is approximately equal to this thing that we're going to call the probability density times delta x, okay? So the probability density p of x times delta x, notice that's an area. And so this should give us a sort of, we should recognize that we're dealing with integrals, okay? And the probability that a point should fall in the interval AB, well, here the probability density could change. So, this is a uniform probability density if it could land anywhere on here. But maybe for some reason, it's more likely for a point to land here. I don't know, maybe there's something attractive over there. If it is more likely for a point to land here for reasons of, having some attractive potential or something, then the probability density is not going to be constant. And so, this p of x delta x is only approximate. To get the actual probability that it lands between any points a and b, so when delta x could be very large, right? If you're looking at, say a large a to b here, well, the probability density could change, and you do an integral. Okay, so this is the definition of a probability density, okay, in a sense. It's the probability that a point will land between a and b. To get that, you'll take the integral of the probability density from a to b. More formally, a probability density is one that satisfies the following. One, that the probability of x being between a and b is equal to the integral from a to b of p of x dx. The probability density must remain positive. We don't want any sort of negative probabilities, and so we impose that condition. And finally, integrating from minus infinity to plus infinity gives us 1. Now, why is that? That's just to say that the probability that, x will lie anywhere on the real line should be 1. Right? I mean, where else is it going to? So that's called the normalization condition, okay? We're just saying that the sum of all the probabilities, all the possibilities, needs to equal 1, okay? And also, we could ask the question of what's the probability that the point x is landing below a certain value t, okay? Arbitrarily, some arbitrary value t, and here we get what's called the cumulative distribution function rather than the probability distribution function. We get the cumulative one, and what we do for the cumulative is integrate from minus infinity to t. And again, this is the probability of having x be below t. So all you're doing is just taking the probability density and integrating from minus infinity to that particular point t. The cumulative distribution function satisfies that p, this capital P, is the antiderivative of lowercase p. Okay, you see that with the integral. P is always increasing. It must, right? Probabilities will increase, and if you take t to infinity, you should get 1. And as you're increasing t, you should increase. The cumulative distribution function should increase. The limit as t goes to infinity is 1. That's just to reflect that the normalization condition above. And the limit as t goes to minus infinity is 0. That's just to say that, that you're not going to have any value below negative infinity. Okay? And the probability that x is between a and b is pb minus pa, which, even if you write these out with the minus infinity notation, it's basically the same that you would get with the probability density being from A to B. Okay? And so that's the same as this over here. And so what we'll do is just subtract. This is basically another way of using the fundamental theorem of calculus. Okay, so this is the antiderivative evaluated at the bounds. And so that's why we use this cumulative distribution function. So let's look at a concrete example. So we're given this probability density here. Okay, this is how it looks. C is left as the sort of height at 0. Okay, we want to find the value of C. And now that's a bit of a weird question, right? Because you would think that should be given. But don't forget, we have the normalization condition. The sum of all possibilities, the probability of all possibilities, should sum to 1. Okay? And so using that, we could integrate this from minus infinity to plus infinity. And here, because this is a piecewise function, we break it up into different intervals. And carrying out that integration, we get the value c. And so we need c to equal the 1 by the normalization condition. We get that value there. Okay, so that fixes C. C must be 1 if this is to be a probability density, because the total area under the probability density should be 1. And so that's how we found C. Find the probability that the score of the game will be positive. Okay? So X is the score of a game, and this is the probability density for X being a particular score of the game. And so we want to find the probability that the score of the game will be positive. Well, what do we do there? Well, the positive, if it's positive, then X is going to land on the positive x-axis. So we just integrate from 0 to infinity. The probability density is 0 past 1, and so all we have to do is integrate from 0 to 1, and we get 1/2. We want to find find the probability that the score will be between minus 0.5 and 0.2. Again, we take the probability density, integrate it from minus 0.5 to 0.2. This is a piecewise function, and so we have to change the function from, when we're integrating the negative values, we use that function there. When we're integrating the positive values, we use negative x plus 1. And we find that it's 0.555 when we carry out those integrations. D, find the cumulative distribution function of p of x. Here we integrate from minus infinity to some arbitrary t. And now this is going to depend on where t falls. If t is below minus 1, well, all we're integrating is 0. If t falls somewhere between minus 1 and 0, then our integral will just have this x plus 1, because we found c was 1. And so we'll integrate from minus 1 to t, because everything from minus infinity is 0 anyway. And so we'll integrate from minus 1 to t, and we'll get that for our cumulative distribution function. What about when t is between 0 and 1? Here we'll integrate to 0, okay? If we integrate to 0, then we'll have minus 1 to 0. We just plug in a 0 in there for that t, and we'll get 1/2, and that's where this 1/2 is coming from, okay? Plus, our integral from 0 to whatever value t here lies between 0 and 1. And so we do that, we carry out, and notice that this is the minus x plus 1 because we're looking at t being between 0 and 1. And we already carried out the area of that. The area of the left side of that is going to be 1/2. And so we get this function here, and we have that 0 is between t and 1 there for that. And finally, for t is greater than 1, well, what you could do is just plug in t equals 1 into this, and you will get 1/2 plus 1/2, or 1. And that's what it should be, because when we normalized, we made sure that the limit as t goes to infinity for the cumulative distribution function would end up being 1. And so for t greater than 1, and there is no area beyond 1, and so that's what we get for the different values of t. We have this cumulative distribution function. Find the probability that a score will be less than 0.5. Again, we could carry out the integral from minus infinity to 0.5, but why would we do that? We already calculated the cumulative distribution function, so all we have to do is just plug in 0.5. Plugging in 0.5, well, where is 0.5? 0.5 is between 0 and 1, and so we're going to use this form. We're going to use this part of the piecewise function, and we will have 1/2 plus negative 1/2 0.5 squared plus 0.5, and we get 0.875. And so that's how we could use integration to help us with probabilities, in particular a continuous set of events.